Hello there, and welcome to the Sleepy Science Channel. Tonight, we are turning our gaze towards the night sky. Not to the stars, but to something you cannot see, cannot feel, and yet cannot escape. Cosmic rays are invisible messengers from exploding stars, from restless black holes, and from corners of the universe so distant their light has traveled for billions of years. They stream toward us at the speed of light, crossing the vast dark between galaxies, only to meet our atmosphere in a silent cascade of energy. Every moment, space is reaching out to Earth, with particles carrying stories from violent and beautiful events far beyond our sky. These travelers have shaped scientific discovery, challenged our understanding of matter, and revealed that our planet is not isolated, but immersed in a cosmic storm of energy. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, there is nothing you need to do but relax. Let your shoulders soften, let your breathing slow, and allow your thoughts to drift as we explore this vast and surprising universe together. Let's begin. Cosmic rays are invisible bullets striking Earth from every direction. They arrive from overhead, from the horizon, and even from beneath your feet after ricocheting through the planet's air. What makes that all directions feeling so uncanny is that space does not behave like a single spotlight. Charged particles wander through tangled magnetic fields between stars, and their paths get scrambled until the sky becomes a sphere of incoming traffic. Scientists map this steady rain with detectors spread across deserts, mountaintops, and rooftops. Each detection is a tiny alarm bell that says something energetic just crossed the solar system and kept going. When many sensors trigger at once, it can mean one visitor struck high above and shattered into a wide footprint of debris. It is a reminder that Earth lives inside an active universe, not a sealed glass dome. Most cosmic rays are just atomic nuclei, stripped bare of electrons. Imagine the heart of an atom, the dense core that normally sits wrapped in a cloud of electrons. In space, violent environments can rip those electrons away, leaving a naked nucleus with electric charge and enormous momentum. Some are the simplest kind, lone protons. Others are heavier, like helium nuclei, or even nuclei of much heavier elements. Because they are charged, they respond to magnetic fields like iron filings near a magnet, curving and spiraling instead of flying straight. That bending hides their birthplaces and turns their arrival into a mystery story. Their stripped state also makes them chemically silent, since chemistry needs electrons. What reaches us is not a molecule or a gas. It is raw nuclear matter, traveling as a fast, compact package of mass and charge, carrying clues about where it has been. A single cosmic ray can carry more energy than a baseball pitch. That sounds impossible until you remember how small a particle is. A baseball spreads its energy across grams of matter. An extreme cosmic ray concentrates comparable energy into something smaller than a speck of dust by more than imagination can hold. When such a particle hits the upper atmosphere, it does not thud. It detonates in physics terms, converting its energy into new particles and motion in a split instant. For scientists, this is a gift. Nature is building a particle accelerator in the sky, one that sometimes outmuscles anything humans have constructed. These rare events are also maddening. They are scarce, unpredictable, and they challenge theories about how any object in the universe could fling a particle to such a stupendous speed. Each one is a tiny, high-energy postcard from an engine we have not fully identified. Our atmosphere protects us by turning cosmic rays into particle showers. If Earth had no air, far more of the incoming particles would strike living tissue directly. Instead, the first collision usually happens high above, where the air is thin but present. The incoming particle smashes into an atmospheric atom, and the impact splinters both, creating a burst of fast fragments. Those fragments hit more atoms, and the chain reaction becomes a widening cascade that fans out as it falls. By the time the shower reaches lower altitudes, much of the original energy has been shared among many secondary particles, each carrying a smaller portion. The sky has effectively diluted a dangerous punch into a scattered spray. This is why the atmosphere is not only our source of breath, it is also a planetary safety blanket that sacrifices itself, collision by collision, so the surface stays habitable. Every clear day is also an unseen display of protective physics. You are being gently showered by cosmic ray particles every minute. Even indoors, even at night, even beneath a roof, some of the secondary particles produced overhead reach the ground. Most pass through you without leaving a trace you would ever notice. That is part of what makes the idea so strange. Your body can be crossed by visitors from space and still feel perfectly ordinary. Detectors make the invisible real. A school laboratory counter can tick along as particles pass through, turning a cosmic process into an audible rhythm. The rate changes from place to place. It rises at higher elevations and falls closer to sea level because there is more air above you to absorb and soften the showers. This steady background is also why engineers and scientists care about shielding, materials, and measurement. It is not about fear. It is about understanding a constant, natural ingredient of life on Earth that most people never think about. Earth's magnetic field bends many cosmic rays away, like a shield. The planet behaves like a giant magnet with invisible field lines that loop from one hemisphere to the other. Charged particles moving through those lines feel a sideways force, and their paths curve. For many incoming particles, that curvature is enough to keep them from reaching the lower atmosphere at all. The strength of the protection depends on the particle's energy and charge, and on the local shape of the field. That is why space weather and magnetism matter for satellites and astronauts, which spend more time outside the thick part of the atmosphere. Even on the ground, the field influences how showers develop and where they are most easily detected. This shielding is not perfect, and it is not a rigid wall. It is a dynamic living system shaped by Earth's interior and by interactions with the solar wind. In a cosmic sense, it is a home defense built from molten metal deep below your feet. Airline crews receive extra radiation because cosmic rays intensify with altitude. At cruising height, there is less atmosphere above the aircraft, so fewer particles have been absorbed and dispersed before reaching that level. The result is a higher dose rate than on the ground, especially on long flights. It is not the kind of exposure that makes a flight feel dramatic. It is measured with instruments, tracked with models, and managed through safety guidelines. Routes, flight duration, and even the strength of Earth's magnetic shielding on a given day can influence the numbers. For frequent flyers and for crew members who spend many hours aloft, this becomes an occupational factor, like noise for a musician or sunlight for a lifeguard. The science is a reminder that altitude is not only about thinner air and wide views. It is also about stepping closer to a natural particle cascade that the atmosphere usually filters for you. Up there, you are living in a slightly louder part of the cosmic conversation. Some cosmic rays began inside exploding stars called supernova. When a massive star ends its life, it can unleash a blast wave that races outward faster than any ordinary wind. That expanding shock front plows into surrounding gas and magnetic fields, stirring them into turbulence. In that chaos, charged particles can be kicked again and again, stealing a little energy each time they cross the moving boundary. Over time, a small population becomes enormously energized. The explosion also enriches space with newly forged elements, which means the cosmic rays born in these environments can include more than hydrogen. They can carry pieces of stellar creation, packaged as fast nuclei. This idea links two awe-filled stories. Supernova light up galaxies and seed planets with elements needed for rocks, oceans, and bones. They may also fling a fraction of that matter back into the cosmos at extraordinary speeds, turning death into acceleration. Every detection is a whisper of a star's final fireworks. Others may come from ravenous black holes in distant galaxies. Some galaxies hide a supermassive black hole that is actively feeding. As gas spirals inward, it heats, glows, and twists magnetic fields into powerful structures. In some cases, narrow jets shoot outward at near light speed, launching energy far beyond the galaxy itself. These jets are not made of swallowed matter returning. They are driven by extreme gravity, rotation, and magnetism working together in a region where physics is pushed to its limits. Inside that maelstrom, particles can be accelerated to tremendous energies and then flung into intergalactic space. By the time any of them reach us, the source may look like a faint smudge in a telescope, or it may be hidden behind dust. Yet the particle still arrives, as if carrying the signature of that feeding frenzy. It is one of the few ways the universe can tap you on the shoulder and say, something colossal is happening far away. In a quiet way, cosmic rays help shape the chemistry of our air. When energetic particles crash into atmospheric molecules, they can knock electrons free and create ions. Those ions do not stay lonely for long. They can nudge nearby molecules into new reactions that would be rarer in perfectly neutral air. High in the atmosphere, this contributes to the complex chain of processes that builds and breaks ozone, changes trace gases, and influences how certain compounds form. It is not a simple one-lever control, and it is not the only driver. Sunlight, wind, and chemistry from Earth's surface all play huge roles. Still, cosmic rays add a steady background of ionization that makes the upper air more electrically active than it would otherwise be. Scientists study this because tiny chemical shifts can matter over long times and large scales. It is another way the universe reaches into our planet's systems, not by drama, but by constant subtle interactions that never completely stop. Victor Hess proved cosmic rays exist by flying a balloon upward. In the early 20th century, many scientists assumed the strange radiation detected near Earth must be coming from the ground itself. Victor Hess decided to test that idea in the boldest way possible. He climbed into balloons and rose high into the sky with delicate instruments, carrying them above the thicker part of the air. If the radiation came mainly from Earth, the signal should have faded the higher he went. Instead, after a certain height, it grew stronger. That result changed the story completely. Something powerful was arriving from above. Hess made several ascents, including one during a near-total solar eclipse, to check whether the sun alone could explain it. The signal remained. The mystery was bigger than daylight and bigger than weather. The human being had gone upward into the sky and discovered that space was sending energy down to Earth all the time. Cosmic rays were first suspected because electroscopes discharged for no clear reason. Before the age of giant observatories and space instruments, the trail began with a simple, stubborn annoyance. Electroscopes were built to hold electric charge, with thin metal leaves that separated when charged and slowly collapsed as the charge leaked away. The problem was that they discharged, even when experimenters tried to isolate them carefully. Better insulation helped, but not enough. It was as if some invisible influence kept ionizing the air and giving charge a path to escape. That irritation became a scientific clue. Researchers carried instruments into caves, onto towers, across lakes, and eventually into balloons, all to find where the effect came from. The beauty of the story is how ordinary the starting point seems. No blazing flash in the heavens announced the mystery. A quiet laboratory device kept misbehaving. From that one small puzzle came the realization that Earth is immersed in a constant rain of high-energy visitors from beyond our world. The term cosmic rays is misleading because most are not light. The name sounds poetic and a little ghostly, as though narrow beams are shining toward us from the stars. That is part of why it's stuck. When the phenomenon was first studied, scientists did not yet know exactly what was arriving. Radiation was a broad idea, and the word ray felt natural. Later, the picture sharpened. Most of these arrivals turned out to be particles with mass, charge, and identity, not light waves like visible light or X-rays. Many are protons. Others are atomic nuclei from helium up to much heavier elements. The old name survived even after the science outgrew it. That mismatch matters because it changes how you imagine the universe. Space is not only sending us energy in the form of light, it is also hurling actual pieces of matter across enormous distances. The phrase may be inaccurate, but it preserves the moment when the mystery was still unfolding and the sky had not yet given up its secret. Primary cosmic rays rarely reach the ground intact. They break apart high above. The first incoming particle from space usually meets its fate far above your head. It slams into an atom in the upper atmosphere with such violence that both are transformed in an instant. New particles burst outward, each carrying part of the original energy, and those particles continue downward until many of them collide again. By the time anything reaches the surface, the first traveler is usually gone as an individual object. What remains is a family tree of descendants. This is one reason studying the original visitor is so difficult. Scientists often have to work backward from the debris, like detectives reconstructing a vanished stone from the pattern of ripples it left in a pond. The atmosphere erases the simplest evidence, while creating a richer spectacle in its place. What began as one nucleus from space becomes a multiplying cascade, and the ground-level signal is really the final chapter of a drama that started far above the clouds. Secondary cosmic rays include muons that can pass through thick rock. Among the many particles created in atmospheric cascades, muons are some of the most astonishing. They're cousins of the electron, but much heavier, and that extra heft gives them remarkable staying power. Instead of stopping quickly in air or being soaked up by ordinary materials, many keep going through walls, soil, concrete, and even substantial layers of rock. At sea level, countless muons are still arriving from showers that began high in the sky. They pass through buildings and bodies with little fuss, which makes them easy to overlook and extraordinary once you notice them. Their existence also reveals something deep about nature. They are unstable and should vanish quickly, yet because they travel so fast, the effects of relativity let many survive long enough to reach the ground. That makes them not just useful particles, but living demonstrations of Einstein's universe, arriving from the sky and proving strange physics with every passing second. Muons made by cosmic rays can be used to scan pyramids non-invasively. Because muons can penetrate stone so effectively, they can act like natural probes for hidden spaces. The idea is elegant. Place a detector in or near a large structure, count how many muons arrive from different directions, and compare the results. dense regions block more. Empty cavities allow more through. With enough patience, those differences can reveal internal features without drilling, blasting, or disturbing priceless wars. This method has been used on pyramids, where every unanswered question carries centuries of fascination. A mysterious void cannot be opened casually, but the sky provides a steady stream of particles that can help map what human eyes cannot reach. The result feels almost magical, though the science is beautifully concrete. Invisible particles born in atmospheric showers pass through ancient stone and help archaeologists glimpse the architecture within. It is a meeting between deep time and modern physics, with the universe lending a hand to the study of human history. The sun also makes cosmic rays, especially during strong solar storms. Not all high-energy particles come from distant stars or faraway galaxies. Our own sun can become an intense local accelerator. During powerful eruptions, magnetic fields near active regions can snap, twist, and reconnect with explosive force. Charged particles are then hurled outward at high speed, and some become energetic enough to count as solar cosmic rays. This turns the familiar daytime star into something more dramatic than a warm source of light. It becomes a nearby particle engine that can affect Earth on human timescales. Satellites, radio communication, navigation systems, and astronauts can all feel the consequences when a major event unfolds. The important thing is scale. These solar particles are not usually the champions of extreme energy seen from deeper space, but they matter because the source is close and the timing can be sudden. In those moments, the sun stops seeming calm and reveals itself as an active, magnetic world with sharp moods. Solar outbursts can briefly reduce incoming galactic cosmic rays at Earth. A solar eruption does not only add energetic particles to near-Earth space, it can also sweep some of the usual background away. When a powerful blast of solar wind and magnetic field moves outward from the sun, it disturbs the space between planets like a fast-moving storm front. Galactic particles trying to enter the inner solar system then encounter a rougher magnetic environment and are scattered or held back more effectively. On Earth, detectors can record a temporary drop in the normal count. Scientists call this a Forbush decrease, and it is one of those wonderful effects that sounds backward at first. A solar event makes the space around us more intense in one sense, yet can reduce the number of particles arriving from the wider galaxy. It shows that Earth is not simply sitting under an open sky. We live inside a changing bubble shaped by the sun, and that bubble can thicken its defenses for a while. Cosmic ray intensity changes with the solar cycle, rising and falling over years. The sun follows a broad rhythm that lasts about 11 years, marked by changing magnetic activity, sunspots, and eruptions. As that cycle climbs toward a more active phase, the solar wind becomes more disturbed, and the magnetic shield filling the solar system grows more effective at deflecting many galactic arrivals. When the sun quiets down again, that shielding eases, and more of the background can slip inward. So the count measured near Earth does not stay perfectly steady from decade to decade. It breathes in opposition to the sun's mood. This long pulse matters to spacecraft planning, radiation studies, and the interpretation of old records locked in ice or tree rings. It also adds a beautiful layer to the story. The particles racing in from the galaxy are shaped not only by remote explosions and deep space fields, but by the waxing and waning activity of our own star. The local star sets the rhythm for a much larger reign. Earth's poles emit more cosmic rays than the equator does. The planet's magnetic protection is not equally strong everywhere. Near the equator, the field does a better job of turning away many lower energy charged particles, because the geometry of the field makes entry harder. Near the poles, the magnetic lines dip downward, and provide easier access routes into the atmosphere. That means polar regions receive a larger share of incoming traffic. Scientists see this clearly in flight measurements, radiation models, and detector records from different latitudes. It also explains why high-latitude air routes can draw special attention during strong solar particle events. Geography, in this case, is tied directly to invisible physics. The map of Earth is also a map of changing cosmic exposure. One part of the world is not simply colder or darker in winter. It is more open to space in a measurable way. The poles are reminders that our planet's magnetic cocoon has weak points, and the sky knows exactly where they are. A cosmic ray air shower can spread across an entire city. One particle from deep space can strike the upper atmosphere and unleash a cascade so broad that detectors miles apart all react to the same event. What began as a single incoming traveler becomes a branching storm of secondary particles, spreading outward as it races down through the air. By the time the shower reaches the ground, it can cover streets, rooftops, fields, and neighborhoods all at once. Scientists build huge detector networks for exactly this reason. A small instrument can catch particles, but a wide array can reveal the footprint of the whole event. The timing matters as much as the count. By measuring when the shower reaches different detectors, researchers can reconstruct the direction and energy of the original arrival. It is astonishing to think that a visitor smaller than an atom's core can create an atmospheric event large enough to wash over a city. The universe can begin with something tiny and end with something vast. Some detectors catch cosmic rays by seeing faint blue Cherenkov light. When certain particles move through a material faster than light can travel through that material, they produce a ghostly blue glow called Cherenkov light. This does not break the cosmic speed limit because light still moves fastest in empty space. Inside air, water, or glass, light slows down, and a very fast particle can outrun that local speed. The result is a brief flash, like the optical version of a sonic boom. Telescopes and specialized detectors can watch for that light when particle showers race through the atmosphere. The flashes are faint and fleeting, so the instruments must be sharp, and the skies often need to be dark and clear. Yet when it works, scientists can use those boo whispers to infer the arrival of an invisible event high above. It is one of the most beautiful tricks in physics. A particle too small to see can still announce itself by making the air glow for an instant. Other detectors use water tanks that flash when particles pass through. In some observatories, the landscape is dotted with large tanks of purified water, each sitting quietly under the open sky like a patient trap for invisible visitors. When fast particles from an air shower plunge through the water, they can generate Cherenkov light inside the tank. Sensitive photodetectors lining the container catch that brief flash and turn it into an electrical signal. One tank alone tells only a small part of the story. Hundreds of them working together can trace the size, direction, and strength of a vast particle cascade. This method is wonderfully direct. You let the shower come to you, and the water records its passing in pulses of light. There is something almost elegant about the simplicity. No giant moving machinery, no dramatic explosion, just still containers waiting for distant violence to arrive and reveal itself. A desert plain filled with quiet water can become one of humanity's most powerful tools for listening to the sky. Cloud chambers once made cosmic rays visible as delicate streaks. Before computer screens filled with digital plots, there were instruments that let people actually watch particle tracks appear before their eyes. A cloud chamber contains supersaturated vapor poised on the edge of condensation. When a charged particle passes through, it leaves behind a trail of ionization, and tiny droplets form along that path. The result is a thin white line that curls, forks, or shoots straight across the chamber like a fleeting signature from the invisible world. In the age before modern particle accelerators, that sight must have felt almost miraculous. Cosmic visitors were no longer abstract numbers on a meter. They became visible motions in real space, happening live in front of the observer. The chamber turned radiation into something theatrical without losing scientific value. Each streak could reveal charge, momentum, or the effect of a magnetic field. It was as though the universe had briefly agreed to write in smoke, allowing human eyes to witness processes far too small to see directly. Early particle physics advanced because cosmic rays revealed new particles first. Before scientists could build machines powerful enough to smash particles together at will, nature was already running the experiment overhead. High-energy arrivals from space were producing collisions in the atmosphere that exceeded what laboratories could manage at the time. Researchers learned to study the debris from those natural impacts, and in doing so, opened a doorway into the subatomic world. New tracks appeared in photographic plates, cloud chambers, and other detectors, hinting at entities no one had predicted clearly. In a sense, the sky served as the first high-energy laboratory. It offered rare events instead of controlled ones, and that made the work difficult. But it also gave physicists access to energies far beyond their equipment. This history matters because it shows how astronomy and particle physics grew together. The study of the very large helped reveal the very small. Long before giant accelerators dominated the field, the atmosphere itself was already delivering discoveries from beyond Earth. The muon was discovered in cosmic rays, and it puzzled everyone. When this particle first appeared in the evidence, it did not fit neatly into the picture scientists were building. It resembled an electron in charge, but it was far heavier, which made it feel like an unexpected duplicate of something nature already had. One famous physicist reportedly asked who had ordered it, and that reaction captures the mood perfectly. The new particle seemed to arrive without explanation, as though the universe had slipped an extra piece into the box. Its discovery forced researchers to accept that the subatomic world was richer and stranger than the simplest models suggested. Later, the muon became deeply useful in particle experiments, precision measurements, and studies of relativity. At first, though, it was a pure puzzle. That is part of what makes its story so compelling. Cosmic rays did not merely confirm existing theories. They brought back surprises. The sky was not just answering questions. It was asking better ones than scientists had known to ask. Cosmic rays helped reveal the positron, antimatter with positive charge. For centuries, matter seemed to be the whole story. Then theory suggested that every particle might have a partner with the same mass and opposite charge. That idea sounded bold, almost too elegant to be real. Evidence arrived from cosmic ray studies, where detectors captured tracks that looked like electrons in many ways, but curved the wrong way in a magnetic field. That curvature was the clue. Here was something light like an electron, yet positively charged. The positron had entered the scene. Its discovery was one of those moments when the universe proves that mathematics was not merely a human game. Antimatter existed. It could be born in energetic processes and detected in the debris from cosmic events overhead. This mattered far beyond one particle. It showed that reality has a kind of mirror architecture, with familiar matter accompanied by opposites. Cosmic rays were among the first messengers to reveal that startling symmetry, and the world of physics was never quite the same again. Some cosmic rays are heavy elements, forged in violent stellar furnaces. Not every incoming particle is a lonely proton. Some are nuclei of much heavier elements, which means they were created in environments capable of building complex atomic matter long before those nuclei were blasted into space. The story begins inside stars, where fusion constructs heavier elements step by step, and continues in catastrophic events such as supernova or other violent outbursts that scatter that matter across the Bayer galaxy. When one of those heavy nuclei reaches Earth as a cosmic ray, it is carrying a record of stellar alchemy. Iron, for example, is not just a common metal in tools and blood chemistry. In this context, it can be a fragment of ancient nuclear history, accelerated across interstellar space and delivered to our detectors. That gives cosmic ray research a poetic depth. Scientists are not merely measuring fast particles. They are sampling matter that was forged in extreme astrophysical furnaces, then launched outward as part of the galaxy's restless circulation of elements. A tiny fraction are electrons, racing close to light speed. Electrons are much lighter than atomic nuclei, and that lightness makes their journey through space especially fragile. They lose energy more easily as they interact with magnetic fields and radiation, which means they cannot usually wander through the galaxy for as long as heavier particles can. That vulnerability turns them into useful clues. When scientists detect high-energy electrons among the arrivals, it suggests the sources may be relatively nearby in cosmic terms, or at least recent enough that the particles have not been drained of energy before reaching us. In other words, these tiny messengers may point toward fresh activity in our galactic neighborhood. Their presence also broadens the cast of characters in cosmic ray studies. The sky is not sending one uniform kind of projectile. It is sending a mixed population, and each type tells a different version of the story. The electrons speak in a more delicate voice, but what they say can be remarkably revealing. Even rarer are antiprotons, created in high-energy collisions in space. An antiproton is the antimatter counterpart of the proton, with the same mass and the opposite charge. Finding these particles among cosmic rays is remarkable because they are not expected to survive easily or exist in large natural reservoirs nearby. Most are thought to arise as secondary products when fast-moving cosmic particles slam into interstellar matter, creating brief showers of new particles in deep space. That makes them precious clues about high-energy collisions far beyond Earth. Measuring how many arrive and how their energies are distributed gives scientists a way to test models of cosmic ray transport and to search for hints of more exotic origins. Some researchers have even asked whether unusual excesses could point toward processes involving dark matter. The challenge is that antiprotons are rare and must be distinguished carefully from ordinary particles. Yet that rarity is part of their allure. Among the crowded traffic of the cosmos, they are like strange mirrored travelers, slipping through from a more elusive side of physics. Supernova remnants can act like natural accelerators called shock fronts. After a star explodes, the blast does not simply vanish into space. It drives an expanding shell into the surrounding gas, and along that moving boundary, a shock front forms. On one side lies material already swept and heated. On the other lies gas that has not yet been struck. Charged particles caught near that frontier can ricochet back and forth across it, scattered by restless magnetic fields. Each crossing can add a little energy, like a skater gaining speed with every well-timed push. Over time, a few particles are promoted from ordinary debris to astonishingly fast travelers. This process gives the wreckage of a dead star a second life as a powerful accelerator. What is left behind is not only a glowing nebula for telescopes to admire. It is also a working machine built from violence, motion, and magnetism, turning stellar ruin into a launch site for some of the fastest matter in the galaxy. Magnetic turbulence can scatter cosmic rays, trapping them inside our galaxy. The Milky Way is threaded with magnetic fields, and those fields are not smooth like clean lines drawn on paper. They are tangled, rippling, and turbulent. For a charged particle trying to cross the galaxy, that disorder matters enormously. instead of flying in a straight line from source to destination, it gets knocked off course again and again, bouncing through a maze of magnetic irregularities. The result is less like an arrow and more like a wanderer lost in fog. This scattering can keep particles roaming the galaxy for immense stretches of time before they finally escape into intergalactic space. That delay changes everything scientists infer from what reaches Earth. It blurs the connection between cause and effect and mixes together contributions from many different sources. In a strange way, the galaxy behaves like both a birthplace and a cage. It creates energetic particles, then holds many of them in a restless magnetic prison. Cosmic rays do not point neatly back to their sources, because fields bend them. If these particles traveled like beams of light, astronomy would be much easier. We could trace each arrival backward along a straight path and ask what object sits at the far end. But charged particles do not grant that convenience. Every magnetic field they cross, whether near a star, between stars, around the sun, or inside our own galaxy, pushes them sideways and curves their motion. By the time they reach Earth, their direction often reflects a long history of detours, rather than a clean line to their birthplace. That makes cosmic ray science feel almost detective-like. Researchers must infer origins from energy, composition, and statistics instead of simple pointing. The particles arrive with tremendous information, yet they also arrive scrambled. This is why the sky can be full of clues and still keep its secrets. The messengers are real, but the return address has been smudged by the magnetic structure of the universe itself. The Milky Way is filled with cosmic rays, carrying energy through interstellar space. It is easy to picture the galaxy as stars, planets, dust, and dark lanes between them. Yet the space between those visible features is not empty in any simple sense. It contains magnetic fields, thin gas, and a sea of fast-moving particles carrying energy across enormous distances. These particles contribute to the pressure within the interstellar medium, alongside gas pressure and magnetic pressure, and that means they help shape the large-scale behavior of the galaxy. They are part of its weather. They drift, diffuse, and interact with matter in places where starlight may be faint, and ordinary intuition begins to fail. This idea transforms the Milky Way from a static collection of shining objects into a living environment full of motion and exchange. The galaxy is not merely decorated with stars. It is permeated by invisible traffic. Energy is constantly on the move, threading through the dark spaces between suns like a hidden circulation system. Cosmic rays heat and ionize interstellar gas, shaping how clouds evolve. Far from stars, vast clouds of gas can be cold and dim, yet they are not perfectly still in a chemical or physical sense. Fast particles passing through can knock electrons off atoms and molecules, creating ions in places where sunlight is too weak to do much of the work. That ionization changes how the gas behaves. It affects electrical coupling to magnetic fields, alters reaction pathways, and adds a trickle of heat to environments that might otherwise cool even further. Over long periods, those effects can influence whether a cloud remains diffuse, contracts under gravity, or fragments into denser regions that may someday form stars. The scale is almost impossible to hold in the mind. A particle accelerated by an ancient violent event can later help determine the condition of a dark cloud, light years away. In that sense, these travelers are not just messengers. They are active participants in the slow, ongoing reshaping of galactic matter. They can trigger chemical reactions in dark molecular clouds where sunlight cannot reach. Deep inside some interstellar clouds, dust books starlight so effectively that ordinary ultraviolet-driven chemistry nearly stops. Yet chemistry does not go silent there. energetic particles can still penetrate and create ions, radicals, and other reactive fragments that would otherwise be scarce. Those products then drive chains of reactions through the cold darkness, helping build surprisingly complex molecules in places that seem almost cut off from energy. This matters because such clouds are nurseries for future stars and planetary systems. The ingredients of later worlds are being altered long before any sun shines on them. In these hidden regions, high-energy particles become substitute sparks, keeping chemistry alive where light has been excluded. There is something beautiful in that arrangement. Even in the most shielded and shadowed pockets of the galaxy, transformation continues. A cloud may look silent from afar, but inside, invisible visitors are stirring the molecular story forward in the dark. Cosmic rays may influence how often lightning starts by seeding free electrons. Lightning is one of the most dramatic phenomena in the sky. Yet the exact moment a bolt begins is surprisingly hard to explain. Thunderclouds can build huge electric fields, but in some cases those fields seem not quite strong enough, by simple estimates, to trigger the discharge we actually observe. One idea is that energetic particles from space help provide the missing nudge. As they pass through the atmosphere, they can free electrons and create conditions that make electrical breakdown easier. In that picture, a storm is already primed, and an invisible visitor helps tip the balance. The idea remains an active area of study rather than a settled conclusion, but that uncertainty is part of its fascination. It suggests that thunderheads may not be acting alone. A flash across the sky could be influenced by processes that began far beyond the weather itself. Even familiar storms may be connected, in subtle ways, to the high-energy traffic of space. The atmosphere's lower layer absorbs many cosmic rays, yet some still reach you. By the time a shower descends into the denser lower atmosphere, much of the original drama has already been spent. Countless particles have collided, decayed, or lost energy on the way down. The lowest layer of air acts like the final, thickest filter, removing many more before they can ever touch the ground. That is why life at the surface is possible under a sky that is constantly being struck from above. Even so, the filtering is not absolute. Some particles still make it through, especially the more penetrating members of the shower. Their arrival is part of the normal background of Earth, present in cities, forests, deserts, and oceans alike. This is a powerful reminder that protection does not mean isolation. Our planet softens the bombardment, but it does not completely seal us off from the larger universe. We live beneath a shield, not beneath a lid. A little of space still gets through. A cosmic ray can strike a detector and mimic a rare signal. Some of the most sensitive experiments in science are searching for events so unusual that a single false alarm can waste enormous effort. A detector may be waiting for evidence of dark matter, a rare nuclear decay, or a faint particle from deep space. Then an unrelated visitor from the cosmic ray background arrives and leaves a signal that looks, at first glance, tantalizingly similar. That is one of the great practical challenges of modern physics. Before you can trust a discovery, you must understand every way nature can impersonate it. Researchers respond with layers of shielding, underground laboratories, timing systems, and veto detectors designed to catch or reject these imposters. In a sense, cosmic rays become both a tool and a nuisance. They reveal fascinating physics, but they also interfere with quieter measurements by barging into the scene uninvited. Even when scientists are studying something else, the universe keeps sending these energetic interruptions from above. Cosmic rays can flip bits in computer memory, causing single event upsets. Inside a computer, information is stored as tiny physical states representing zeros and ones. In most situations, those states remain stable, but not always. When an energetic particle passes through a microelectronic component, it can deposit enough charge to alter one stored value. A 0 becomes a 1, or a 1 becomes a 0, and the result is called a single event upset. It does not mean the machine is haunted or poorly built. It means modern electronics are so small and so precise that a solitary particle from a cosmic shower can sometimes disturb them. This matters especially in aircraft, satellites, and critical systems where even a brief glitch can have consequences. Engineers use error correction, shielding, and careful design to reduce the risk. The idea is thrilling and unsettling in equal measure. A message that began with a violent event in space can end by nudging a memory cell on Earth and changing a computation by 1 bit. Spacecraft electronics need shielding because cosmic rays can cause glitches. Once a machine leaves Earth, it also leaves behind much of the natural protection that keeps delicate electronics safer at the surface. In orbit or on deep space missions, fast particles can strike chips, sensors, and control systems directly. A single hit may create false signals, corrupt data, or briefly confuse a computer that was otherwise working perfectly. That is why spacecraft are designed with protection in layers. Engineers add shielding where weight allows, choose radiation-tolerant components, and build in redundancy, so one upset does not become a mission-ending failure. Sometimes the goal is not to stop every particle, because that would demand impossible mass. The goal is survival. A spacecraft must keep thinking clearly while crossing a noisy environment filled with invisible impacts. That practical challenge gives cosmic rays a new role in the story. They are not only a subject for astronomers. They are active hazards that mission designers must respect before any probe can safely explore the solar system. High-energy cosmic rays pose a serious challenge for long, deep space trips. For astronauts traveling far from Earth, the danger is not only launch, landing, or mechanical failure. It is also the steady and sometimes intense radiation environment between worlds. Some incoming particles are energetic enough to slice through ordinary shielding and damage living tissue at the cellular level. That raises concerns about cancer risk, nervous system effects, and harm to blood-forming organs during long missions. The difficulty is cruelly simple. Better shielding often means more mass, and more mass means harder launches and higher cost. Yet some kinds of matter can also produce secondary particles when struck, which complicates the solution. Mission planners must think about habitat design, storm shelters, travel time, and even whether future crews can be protected by water, fuel, or specially chosen materials. The dream of going far into space is not blocked by lack of courage. It is blocked, in part, by invisible projectiles crossing the same emptiness our spacecraft must cross. Mars has weaker protection than Earth, so cosmic rays are a bigger hazard there. Earth enjoys two major defenses at once: a thick atmosphere and a global magnetic field. Mars offers much less. Its atmosphere is thin, and it no longer has a planet-wide magnetic shield comparable to ours. That means energetic particles can reach the Martian surface more easily, giving future explorers a harsher radiation environment than they would face on Earth. The danger matters for every part of human planning. Where should habitats be built? How much shielding can be carried? Would crews spend safer hours underground, perhaps inside lava tubes or beneath piled regolith? Even robotic missions must consider what years of exposure can do to electronics and instruments. The planet may look inviting in photographs with deserts, polar caps, and familiar day length, yet the invisible reality is much less friendly. To live there would mean settling a world where the sky allows more of space to reach the ground. Mars is not only distant, it is exposed. The Moon's surface receives more cosmic radiation than most places on Earth. Standing on the moon would mean standing on a world with almost no atmosphere and no global magnetic cocoon to soften the particle environment. Day after day, the surface is exposed to galactic arrivals, solar particles, and secondary radiation produced when those particles strike the ground itself. On Earth, people can forget the cosmic background because air and magnetism do so much silent work. On the moon, that hidden protection is gone. This changes what it means to build a base there. Walls matter more. Buried habitats become appealing. Even where astronauts store supplies could double as part of a protective shell. The danger is not cinematic in the ordinary sense. It is not a visible beam sweeping across the landscape. It is a constant, penetrating presence that adds up over time. That makes the moon a humbling place. It looks calm and still, yet in radiation terms, it is much more exposed to the wider universe than home. Cosmic rays can create neutrons in the air, which scientists can measure at ground level. When high-energy particles crash into atoms in the atmosphere, the wreckage is not limited to charged fragments. Neutrons can also be produced, and those are especially interesting because they carry no electric charge. That means magnetic fields do not steer them the way they steer protons or electrons. Some of these neutrons continue downward, and enough can reach the surface that scientists can monitor them from the ground. This is a remarkable idea when you stop to feel it fully. A collision high in the sky can generate neutral particles that later help researchers track what is happening in space. The signal reflects both the incoming cosmic environment and the changing influence of the Sun and Earth's magnetic conditions. In effect, the atmosphere becomes part of the measuring instrument. It transforms unseen arrivals into something that can be counted in observatories on the ground. The sky is not merely being struck. It is also helping produce the evidence. Neutron monitors quietly track cosmic ray changes worldwide every day. Across the world, stations equipped with neutron monitors keep watch with a kind of patient consistency that feels almost monastic. They do not chase headlines or wait for spectacular images. They count. Day after day, year after year, they record how many secondary neutrons are arriving, building a long global record of cosmic ray behavior near Earth. Because many stations are spread across different latitudes and altitudes, the network can reveal how solar disturbances, magnetic conditions, and larger cycles affect the particle environment. During unusual events, these monitors may show sudden dips or surges that help scientists understand what the Sun and interplanetary space are doing. There is something beautiful about that quiet labor. A worldwide web of instruments listens to consequences of distant astrophysical processes without fanfare. The data they gather supports space weather studies, radiation research, and historical comparisons. In a very real sense, these monitors are Earth's daily pulse check on how open we are to the cosmos. Cosmic rays help create carbon-14, the clock behind radiocarbon dating. High in the atmosphere, energetic particles can set off reactions that transform ordinary nitrogen into carbon-14, a rare radioactive form of carbon. That isotope then becomes part of carbon dioxide, enters plants through photosynthesis, and moves through food webs into living things. While an organism lives, it keeps exchanging carbon with the environment. After death, that exchange stops, and the carbon-14 already present begins to decay at a known rate. This is what makes radiocarbon dating possible. Archaeologists can estimate the age of wood, bone, cloth, and other once-living materials by measuring how much remains. The astonishing part is the chain that connects the result to space. A seed buried beside an ancient fire, a scrap of woven fiber, or a human artifact from long ago may owe its date to particles that struck the atmosphere from beyond Earth. Cosmic rays are not only astrophysical curiosities. They help humanity measure history itself. They also create beryllium-10, which records past solar activity in ice. Another rare isotope born from atmospheric particle reactions is beryllium-10. After it forms, it can attach to aerosols and eventually fall with snow or rain, where some of it becomes locked into glaciers and ice sheets. Layer by layer, that deposition builds a natural archive. When scientists drill ice cores and measure the changing amounts preserved in different layers, they gain clues about how the cosmic ray flux changed in the past. Because solar activity helps regulate how many galactic particles reach Earth, the record can be used to infer long-term changes in the sun's behavior. The frozen layers become a kind of indirect space diary written in chemistry. That is what makes this isotope so captivating. Snow that fell thousands of years ago may still carry a trace of how open the solar system was to incoming particles at that time. Ice is not only frozen water. It is a slow, stratified memory of our cosmic environment. Tree rings can preserve cosmic ray history through changes in carbon-14. Each year, a tree adds a new ring, and in doing so, it captures carbon from the atmosphere available during that growing season. Because carbon-14 production depends in part on incoming high-energy particles, shifts in its abundance can become imprinted in those annual layers. This allows scientists to compare ring-by-ring records across time and detect changes linked to solar activity, magnetic conditions, or even unusual bursts in atmospheric isotope production. The method is powerful because trees provide yearly resolution and can be tied together across long spans using overlapping chronologies. A forest, in that sense, becomes an archive of space weather and cosmic history, recorded in wood one season at a time. There is something deeply moving about that connection. A living organism rooted in soil can preserve a signal from events far beyond Earth. The rings do not merely mark age. They can also whisper how the sky was behaving while the tree was growing. Cosmic rays can make new isotopes inside meteorites, revealing how long they traveled. A meteorite drifting through space is exposed to energetic particles for ages before it ever falls to Earth. Those particles can strike the atoms inside the rock and create new isotopes through nuclear reactions. By measuring which isotopes are present and in what amounts, scientists can estimate how long the object was exposed during its journey as a smaller body in space. This is called a cosmic ray exposure age, and it offers a timeline different from the age of the rock itself. A meteorite may have formed billions of years ago inside an asteroid, then been knocked loose much later by a collision, and only after that begun its final exposed voyage. The isotope record helps separate those chapters. That makes each recovered meteorite more than a fallen stone. It is a traveler with a measurable travel history. Space leaves marks on matter, and careful laboratory work can read how long that long, silent voyage lasted. A shower's particle spread depends on the energy of the first impact. When an incoming particle strikes the upper atmosphere, the violence of that first collision helps determine everything that follows. A lower energy arrival may produce a modest cascade, narrow enough that only a small region on the ground notices it. A far more energetic arrival can generate a much broader spray, with descendants spreading outward as they multiply and fall. The first impact is like the opening move in a long chain reaction. It sets the scale, the reach, and the character of the event. Scientists use that relationship to estimate the power of something they never saw directly. They read the pattern left behind. How wide was the footprint? How many particles survived to lower levels? How were they distributed across the detector array? From that evidence, they can reconstruct the force of the initial strike. One collision high above the clouds can decide whether the event stays local or becomes a spectacle spread across the landscape. Some showers create radio pulses, which modern arrays can listen for. Not every cosmic event in the atmosphere has to be watched with light or counted with ground particles. Some cascades also produce brief radio signals, and that allows scientists to listen as well as look. As fast-charged particles rush through the atmosphere, their motion in Earth's magnetic field and the imbalance of charge within the shower can generate a short pulse of radio emission. It lasts only an instant, yet sensitive antenna arrays can catch it and use it as evidence that something energetic has just torn through the sky. This is a wonderfully modern twist in the story. The atmosphere becomes not just a collision zone, but a temporary transmitter. Researchers can spread antennas across large areas and study the shape, timing, and strength of the pulse to learn about the event that created it. The sky does not stay silent when these invisible visitors arrive. Sometimes it gives off a whisper in radio waves. The Pierre Auger Observatory studies the most extreme cosmic rays on Earth. In Argentina, across a vast stretch of open land, scientists have built one of the grandest instruments ever devoted to these particles. The Pierre Auger Observatory covers an immense area with detectors spread far apart, because the rarest and most powerful events demand a net cast on a huge scale. It combines surface detectors with telescopes that watch the atmosphere itself, allowing researchers to compare what reaches the ground with what glows overhead during a shower. That dual view helps reveal both energy and structure. The observatory is named after a physicist who helped uncover the existence of extensive air showers, and the site honors that legacy by chasing the most extraordinary examples nature can provide. There is something thrilling about the scale of it. To study a particle smaller than an atom's core, humanity built an observatory large enough to stretch across a landscape. The tiniest messengers require one of the biggest listening posts. The telescope array also hunts ultra-high energy cosmic rays in wide skies. In Utah, another major experiment watches for the rarest visitors, using a broad desert setting as its stage. The telescope array combines ground detectors with fluorescence telescopes that observe the faint glow produced when showers excite nitrogen in the atmosphere. That means scientists are not only catching the particles that survive to the surface, they're also watching the sky briefly light up along the shower's path. Together, those measurements help reconstruct the direction, strength, and nature of the original arrival. The observatory plays a crucial role because the rarest events are too important to leave to one site alone. Independent measurements, different hemispheres, and different methods all strengthen the search for patterns in the data. The wide skies of the American West become part of the instrument. Empty land, dark nights, and patient detectors join forces to study particles so uncommon that every confirmed event feels like a message rescued from extraordinary odds. These extreme events are so rare that detectors watch huge areas for years. For ordinary cosmic ray studies, smaller instruments can record a steady stream of activity. At the highest energies, that abundance disappears. The most extreme arrivals are so scarce that a detector may wait a long time for one truly remarkable event. That scarcity shapes the entire field. Scientists must build experiments over enormous areas, maintain them for years, and accept that patience is part of the method. You cannot command these particles to appear on schedule. You can only keep watch and be ready when nature finally delivers one. This makes each detection feel precious. It is not just another data point. It is a rare encounter with a process so powerful and so distant that it may only announce itself occasionally. There is a strange grandeur in that slowness. Modern science often feels fast and abundant, yet here it depends on endurance. Vast observatories wait under open skies for moments that may be separated by months or longer. ultra-high energy cosmic rays challenge our understanding of cosmic accelerators. Scientists know several ways nature can energize particles, but the most extreme arrivals seem to demand engines of almost unreasonable power. It is not enough to imagine a violent place. The source must also have the right size, magnetic strength, and conditions to keep a charged particle confined while it gains energy, instead of escaping too soon. That requirement rules out many familiar objects and leaves only a short list of the universe's most formidable environments. Even then, the problem is not fully solved. Some candidates look promising on paper, yet struggle to explain the very highest energies cleanly. Others may accelerate particles well, but not in the numbers that observations suggest. This is why the topic remains so captivating. These particles are not only fast, they are accusations. They tell us that somewhere in the universe, natural accelerators are operating at a level our theories still wrestle to explain. Each extreme detection is a challenge delivered straight to astrophysics. The highest energies suggest sources beyond our galaxy, far into deep space. But more modest energies, the Milky Way may supply many of the particles that reach us. At the very highest end, the story appears to change. Particles with truly extraordinary energies are difficult to explain using ordinary galactic sources, and their behavior hints that they may come from beyond our own star system's larger home. That possibility stretches the imagination immediately. It means a single arrival at Earth may have begun in another galaxy altogether, launched by an object so powerful that it can send matter across the gulf between galaxies. The journey would cross intergalactic space, where matter is thin and distances are staggering. By the time the particle arrives, its source may be millions of light years away. That thought gives these events an almost mythic scale. Yet the evidence is grounded in careful measurement and hard constraints. Some of the most energetic particles that touch our planet may be emissaries from realms far outside the Milky Way. At extreme energies, cosmic rays can collide with background light and lose energy. Intergalactic space looks empty to human eyes, but it is filled with ancient light. The universe is bathed in a faint background of photons left from long cosmic history, and extremely energetic particles cannot ignore them. At ordinary energies, a fast proton can cross space with little consequence from that photon sea. At sufficiently high energies, though, the particle sees those photons differently. In effect, the encounter becomes energetic enough to trigger new interactions, and some of the traveler's energy is lost in the process. This means the universe itself places obstacles in the path of the most extreme arrivals. Deep space is not an open highway for them. It is a medium with a hidden toll. That idea is astonishing because it links the tiniest particles to the largest scales. A single proton on a grand journey can be slowed not by hitting a star or a planet, but by colliding with the faint leftover light that fills the cosmos. This limit helps explain why the very highest energy rays are scarce. If the universe allows extreme particles to lose energy while crossing vast distances, then only certain sources can still send them to us at their full strength. They must be both powerful and relatively nearby in cosmic terms. Otherwise, the journey itself robs them of too much energy before they arrive. This creates a natural cutoff in what Earth should receive, and that helps explain why the most astonishing events are not only rare because their sources are uncommon. They are also filtered by the universe during travel. In a sense, distance becomes part of the detector. A source too far away cannot easily send its most extreme particles to us intact. This is one of the most elegant ideas in the whole subject. The emptiness between galaxies is not truly passive. It edits the message. By the time the particle reaches our atmosphere, The universe has already decided which energies are likely to survive and which are not. Some cosmic ray clues come from how showers develop, not just how often. Counting events is useful, but the shape of each event can be even more revealing. Scientists study where a shower reaches its maximum, how quickly it spreads, and which kinds of particles dominate at different stages. Those details can hint at the nature of the original arrival. A lighter particle and a heavier nucleus do not always produce identical cascades, even if their total energy is similar. Their showers can grow differently in the atmosphere, and that difference becomes a clue about composition. In other cases, the structure of the event can test models of high-energy interactions that cannot be reproduced fully in laboratories. This is where the science becomes almost forensic. Researchers are not just asking how many visitors came. They are asking how each one behaved as it died in the sky. The atmosphere becomes both target and storyteller. Its response preserves traces of the incoming particle's identity long after the particle itself has disappeared. The atmosphere acts like a giant calorimeter, measuring energy by destruction. Physicists use calorimeters to measure energy by forcing particles to crash, scatter, and spend themselves inside carefully designed material. Earth already has a version of that instrument hanging above our heads. When a high-energy visitor plunges into the atmosphere, its energy is not read from a label. It is revealed by what the particle does as it breaks apart and drives a growing cascade through the air. The size of the shower, the depth at which it reaches full strength, and the debris that survives lower down all carry information about the original impact. In that sense, the sky becomes an enormous measuring device built from nitrogen, oxygen, and altitude. What makes this so beautiful is the scale. A technique born in laboratories becomes planetary. Instead of constructing a chamber around the particle, nature provides 1,000 of meters deep. The incoming particle is destroyed, yet in that destruction, it tells us how powerful it was. Cosmic ray particles can penetrate deep underground, even into mines. Going underground feels like leaving the sky behind, yet some particles still follow. Among the most persistent are muons, which can travel through impressive thicknesses of rock before finally losing their energy or decaying. That means deep shafts, tunnels, and mines are not completely cut off from the cosmic world above. Even far beneath the surface, detectors can still record the passage of these visitors from atmospheric showers. The effect is eerie when you picture it clearly. A particle born high above the clouds can cross open air, roofs, soil, and stone, then slip through a chamber carved by human hands far below ground. This penetrating ability is one reason underground science must be designed so carefully. Depth helps enormously, but it does not create perfect silence. The universe still finds a way in. Rock can muffle the cosmic conversation, yet certain particles speak loudly enough that their message survives the descent into the Earth. Underground labs still see muons, so they use heavy shielding and veto detectors. The reason many rare event experiments are built underground is simple. Scientists want the quietest possible environment, one where a truly unusual signal can stand out. Depth removes much of the cosmic background, but not all of it. Muons still penetrate surprisingly far, and when they pass through or near a detector, they can create secondary effects that imitate the very events researchers hope to find. To fight that problem, underground laboratories add more than just rock overhead. They surround detectors with layers of shielding made from carefully chosen materials, and they install veto systems that flag suspicious intrusions. If a muon passes at the wrong moment, the event can be marked and excluded. This creates a kind of scientific discipline, almost like guarding a vault. The treasure is a rare signal, and every possible intruder must be recognized. Even underground, the cosmos remains present enough that experiments need defenses worthy of a siege. Deep water and deep ice help scientists separate cosmic ray backgrounds from rare events. Some of the world's most ambitious detectors are hidden not under mountains, but inside dark natural volumes of water or ice. These environments provide vast amounts of transparent material, and they also place the instruments beneath a protective overburden that filters much of the ordinary cosmic clutter from above. That matters when scientists are hunting elusive particles such as neutrinos, which can pass through planets with almost no interaction. The trick is to reduce the more common background enough that truly rare events can stand out. When a fast particle or secondary product moves through the water or ice, it can create flashes of light that sensors capture. From the timing and pattern of those flashes, researchers reconstruct what happened. The setting itself becomes part of the method. A deep lake, the ocean, or ancient Antarctic ice can serve as both shield and detector. Nature supplies the bulk material, and science turns that hidden darkness into an observatory. Some observatories use the moon as a cosmic ray shield, creating a shadow. The moon has no need to emit a signal for this trick to work. Its value lies in simple blockage. Because it physically stands in the way of some incoming charged particles, detectors can sometimes observe a slight deficit in events from the moon's direction. That missing patch is called the moon shadow. It is a subtle effect, not a dramatic black hole in the data, because cosmic rays are bent by magnetic fields before they arrive. Even so, the deficit can be measured, and it becomes a powerful tool. The idea feels wonderfully counterintuitive. Scientists study particles from the sky by noticing where they do not appear. The moon becomes a giant reference marker, not by shining more brightly, but by stealing a small portion of the incoming flux. In a field full of scattered trajectories and invisible arrivals, that absence is precious. Sometimes the most useful signal is not an extra event, but a carefully measured lag. That moon shadow helps calibrate detectors and confirm their pointing. Once the deficit from the moon is detected, it can be used as a test of how well an instrument understands the sky. If the shadow appears where it should, and with the expected shape, that tells researchers their detector's pointing and angular resolution are behaving properly. If the shadow is displaced, broadened, or otherwise distorted, the data can reveal how magnetic bending or instrumental effects are influencing the measurements. In this way, the moon becomes a cosmic checkpoint. It offers a dependable target against which a detector can prove its accuracy. There is real elegance in using a familiar object for such an unfamiliar purpose. Most people think of the moon as a light in the night sky, a calendar marker, or a source of tides. Here, it becomes a calibration tool for invisible particles. A celestial body we have admired for ages quietly helps modern observatories learn whether they are aiming true. Cosmic rays can be focused by solar magnetic fields in complex ways. The space around the sun is not a calm vacuum. It is threaded with moving magnetic structure, carried outward by the solar wind, bent into broad patterns by the sun's rotation, and constantly reshaped by eruptions and changing activity. Charged particles entering that region do not simply drift through untouched. Their paths can be redirected, scattered, and in some cases funneled into patterns that raise or lower the intensity seen at particular locations. The result is not a perfect lens in the familiar optical sense, but it can still resemble focusing or defocusing in its effects. This makes the inner solar system a dynamic magnetic landscape, one where incoming particles respond to invisible architecture on a grand scale. What reaches Earth, therefore, depends not only on distant astrophysical sources, but also on the structure of space carved by our own star. Even before particles meet the atmosphere, the sun has already had a chance to reshape the journey. A strong solar storm can cause a sudden jump in ground-level radiation. Most solar activity changes the particle environment in space more than it changes conditions at the surface. Yet on rare occasions, an especially powerful event can accelerate particles so effectively that the secondary radiation produced in the atmosphere rises enough to be detected by ground instruments. These episodes are called ground-level enhancements, and they are among the most dramatic links between solar violence and measurements made on Earth. Neutron monitors and related detectors can register the increase, revealing that a burst from our star has briefly altered the particle rain reaching the surface. It is an astonishing chain of cause and effect. A magnetic eruption on the Sun sends energetic particles racing across interplanetary space, and hours later, instruments on Earth notice the difference. The event does not turn the world into a danger zone for everyday life at the surface, but it does show how directly the Sun can, at times, reach down into our measurements from afar. Pilots sometimes reroute flights during solar particle events for safety. Aircraft cruising near the poles or at high altitude occupy a part of the atmosphere where radiation exposure is higher than it is on the ground. During a major solar particle event, that exposure can rise further, especially along routes where Earth's magnetic protection is less effective. In those circumstances, airlines and aviation authorities may consider changing flight paths, adjusting altitude, or taking other steps to reduce risk for crew, passengers, and communication systems. This is one of the clearest ways high-energy space physics enters ordinary human logistics. A decision made in an operations center on Earth may trace back to an eruption on the Sun and to models of how energetic particles are moving through the atmosphere. It is a reminder that modern travel is not only shaped by weather, fuel, and geography. It is also shaped, at times, by conditions in near-Earth space. The sky above an airliner is part of the Sun's wider domain. Cosmic ray exposure varies by latitude, altitude, and solar conditions together. There is no single number that describes everyone's experience of this radiation environment. Where you are on Earth matters. How high you go matters. What the Sun is doing matters too. At low altitude near the equator, the atmosphere is thick overhead and the magnetic shielding is relatively strong, so exposure is lower. Climb to a mountain, board a long-distance flight, or move toward polar regions, and the balance changes. Then fold in solar activity, which can either suppress some incoming galactic particles over long cycles or add energetic solar particles during storms. The final pattern is a layered one, shaped by Earth and Sun together. This makes the subject feel wonderfully alive. Radiation from space is not a fixed backdrop painted onto the world. It rises and falls with geography, weather above the weather, and the changing magnetic influence of our star. The planet is not passively bathed in it. The experience depends on where and when you stand. Earth's magnetosphere traps some charged particles, falling radiation belts. Earth is wrapped in a magnetic field that does more than deflect incoming particles. It can also capture some of them and hold them in looping paths above the planet. These trapped particles bounce between hemispheres and drift around Earth, building vast donut-shaped zones of radiation known as the Van Allen belts. The image is almost unbelievable at first. Our planet is not only sheltered by magnetism, it is also surrounded by invisible reservoirs of energetic particles circling in space. Some are fed by the solar wind. Others come from cosmic interactions that add fresh particles to the system. For satellites, astronauts, and instruments, these belts are not abstract textbook features. They are real environments that can damage electronics and shape mission design. Earth, in other words, wears a kind of electrical weather system around itself. It is one more sign that the space near home is active, structured, and far less empty than it appears. The South Atlantic anomaly exposes satellites to extra radiation from trapped particles. There is a region over the South Atlantic where Earth's inner radiation belt dips closer to the planet than it does in many other places. As a result, satellites passing through that zone can experience a harsher particle environment than their altitude alone might suggest. Instruments may be switched off temporarily, data can become noisier, and engineers design missions with that passage in mind. What makes this so fascinating is that it turns a broad global magnetic field into something uneven and local. Space is not equally hazardous everywhere above Earth. Certain regions are much rougher than others, and the South Atlantic anomaly is one of the most famous examples. A spacecraft can orbit through otherwise routine conditions, then enter this invisible patch and suddenly face greater radiation stress. It is like discovering that the planet's magnetic umbrella has a sagging place where the weather leaks closer to the surface than expected. Cosmic rays can generate glowing auroras indirectly by energizing the upper atmosphere. Auroras are most strongly associated with particles guided by Earth's magnetic field from the solar wind. Yet high-energy particles from beyond can also play a role in energizing the upper atmosphere. When cosmic visitors or the secondary cascades they trigger interact with atoms and molecules high overhead, they can contribute to ionization and excitation. Those excited atoms later release light as they relax, adding to the complex electrical life of the upper air. This does not mean every aurora is driven by cosmic rays, or that the familiar northern lights are secretly a cosmic ray phenomenon in disguise. The story is subtler and more interesting than that. The upper atmosphere is an active stage where many particle populations can leave effects, and cosmic rays are among the players capable of stirring it. Even the sky's great luminous curtains are connected, however indirectly, to the broader traffic of energetic matter moving through space. High-altitude balloons still carry instruments to measure cosmic rays above most air. There is something wonderfully old-fashioned and elegant about sending science upward beneath a balloon. Long after rockets and satellites transformed exploration, high-altitude balloons remain valuable because they can lift instruments above much of the atmosphere at comparatively low cost and with remarkable flexibility. At those heights, detectors encounter a stronger and less filtered particle environment than they would near the ground, which makes them excellent tools for studying atmospheric cascades, solar events, and the changing radiation field. The flights can last for hours, days, or sometimes longer, drifting with winds while quietly collecting data. Balloons also preserve a link to the earliest chapters of cosmic ray discovery, when brave researchers first carried instruments skyward to find out whether radiation really increased with altitude. Today, the technology is far more refined, yet the essential idea is the same. To understand what reaches Earth, sometimes the best move is simply to rise and meet it. Instruments in space can measure primary cosmic rays before the atmosphere breaks them. At the surface, scientists usually study the descendants of the original arrivals. In space, detectors can intercept the primary particles themselves before Earth's atmosphere smashes them apart into complex showers. That difference is profound. It means researchers can measure charge, energy, and composition more directly and can sort different particle types with much greater clarity than ground-based techniques often allow. Space becomes the cleanest place to catch these travelers in their original state. The challenge, of course, is that instruments must survive vacuum, temperature extremes, and constant radiation while operating with great precision. Yet the reward is extraordinary. Instead of reconstructing a story from atmospheric debris, scientists can examine the incoming messengers before the first collision erases their identity. It is the difference between studying footprints after a crowd has passed and meeting the traveler at the gate. Space instruments let us greet the particles before Earth transforms them. The Alpha Magnetic Spectrometer studies cosmic rays from the International Space Station. Mounted on the International Space Station, the Alpha Magnetic Spectrometer is one of the most ambitious particle detectors ever placed in orbit. It was built to identify and measure different kinds of cosmic particles with exquisite precision while they pass through a magnetic field and a stack of specialized detectors. By tracking how those particles curve and how they deposit energy, the instrument can distinguish protons, nuclei, electrons, positrons, and other rarer species. That turns the station into more than an outpost for astronauts. It becomes a long-running observatory for high-energy matter arriving from space. The beauty of the project lies in its patience and its location. Day after day, orbit after orbit, it samples the particle environment above the atmosphere where the original arrivals can still be studied directly. This is frontier science attached to a human habitat, with astronauts circling Earth while an advanced detector quietly reads the traffic of the cosmos beside them. Precise cosmic ray measurements test ideas about dark matter signatures. Dark matter remains one of the great unknowns of modern physics. We infer its gravity, yet we still do not know what it is made of. One possibility is that dark matter particles might occasionally destroy each other or decay, producing ordinary particles that then appear in cosmic ray data as unusual excesses or patterns. That is why precision matters so much. Scientists are not merely counting particles. They're looking for tiny deviations from expected backgrounds, subtle fingerprints that might hint at something entirely new. The challenge is formidable because ordinary astrophysical sources can imitate exotic signatures, and nature rarely labels its clues. A bump in a spectrum may be revolutionary or completely mundane. Even so, the search is thrilling. It means measurements of particles zipping through space could help reveal the identity of the invisible matter thought to dominate the universe's mass. Cosmic ray detectors, in this sense, are also tools for one of cosmology's deepest mysteries. Unexpected positron patterns in cosmic rays sparked big debates in physics. When experiments began measuring positrons in greater detail, scientists found patterns that did not fit the simplest expectations. At certain energies, there seemed to be more of these antimatter particles than standard background models predicted. That result immediately opened multiple possibilities, and the debates were intense. Perhaps nearby astrophysical sources such as pulsars were producing extra positrons and sending them into interstellar space. Perhaps something more exotic was at work. Perhaps the data were exposing hidden weaknesses in existing transport models. What mattered was not just the numbers, but the fact that the cosmos had become argumentative. The observations forced theorists to sharpen their ideas and challenged experimentalists to measure with even greater care. This is one of the most exciting moments in science, when a clean expectation meets stubborn reality, and reality refuses to behave. A surplus of tiny antimatter particles became a pressure point where astrophysics, particle physics, and imagination all collided. Some theories predict antimatter regions in space, yet cosmic rays show little evidence. If large regions of the universe were made of antimatter, then boundaries between matter and antimatter domains could produce striking signatures, and some antinuclei might eventually reach our detectors. In principle, cosmic ray studies offer a way to test that possibility. Scientists have searched especially hard for heavier antinuclei, because finding even a few convincing examples beyond the lightest antimatter particles would be astonishing. So far, the evidence remains extremely sparse. That absence matters. It suggests that if antimatter regions exist at all, they are not nearby, and not mixing with ordinary matter in ways that would easily reveal themselves through the cosmic rays reaching Earth. The result is a beautiful example of how science learns from silence. Not finding something can still reshape our picture of the universe. A sky largely lacking anti-nuclei tells us that the cosmos, at least in the parts we sample this way, seems overwhelmingly built from ordinary matter. Cosmic rays reveal how much matter lies between stars through their slowing and breakup. As energetic particles travel through the galaxy, they do not move through perfect emptiness. Now and then they collide with atoms in interstellar gas, lose energy, or shatter into lighter fragments. Those changes accumulate, and by studying the altered composition of the particles that finally reach us, scientists can estimate how much material they have crossed on their journey. It is a clever and indirect kind of cartography. No one is stretching a ruler between the stars. Instead, researchers read the wear and damage carried by the travelers themselves. Certain fragments are especially informative because they are produced when heavier nuclei are broken apart in flight. Their abundance tells us how much interstellar matter the particles likely encountered before arriving. In that sense, cosmic rays behave like messengers whose clothes are dusty from the road. By examining the scuffs and tears, we learn something about the path. Even the emptiness between stars leaves marks on what passes through it. Many cosmic rays are protons, simple hydrogen nuclei traveling alone. The most common travelers in this story are also the simplest. A proton is the nucleus of hydrogen, just a single positively charged particle without any orbiting electron. That simplicity is part of its power. Hydrogen is the most abundant element in the universe, so when nature accelerates matter to extreme speeds, these lone nuclei are often the easiest cargo to launch. They are small, durable, and everywhere. In a way, that means much of cosmic ray science begins with stripped-down atoms of the element that filled the early universe and still fuels the stars. There is something elegant about that. The grand violence of supernova remnants, stellar winds, and active galaxies often sends out the simplest building block of all. The proton can cross immense distances, survive tangled magnetic regions, and eventually strike our atmosphere with enough force to start a cascade. The smallest nucleus becomes one of the great long-distance messengers of the cosmos. Helium nuclei are the next most common, showing how stars build elements. After hydrogen nuclei, helium nuclei appear again and again in the incoming mix, and that is a clue with deep roots in cosmic history. Helium is the next great step in the universe's elemental story. It was made in large quantities very early on, and stars continue to produce it through fusion as they turn hydrogen into something denser and more tightly bound. When helium nuclei arrive as fast-moving particles, they remind us that cosmic rays are not random debris. They reflect the actual ingredients of the universe. These particular nuclei are sturdy and relatively abundant, which helps them survive long journeys through space. They also connect the subject to stellar evolution in a very direct way. The same process that makes stars shine also helps stock the cosmos with one of the most common components found among these particles. A helium nucleus in a detector is a tiny relic of the universe's great habit of building from the lightest beginnings. Heavier nuclei in cosmic rays mirror the ingredients of our solar neighborhood. When scientists measure the heavier atomic nuclei among these arrivals, they find something wonderfully revealing. The mixture is not wildly alien. Broadly speaking, it resembles the material composition of the region of the galaxy where our sun lives, with recognizable contributions from elements forged in earlier generations of stars. That does not mean the match is perfect in every detail, because acceleration and survival can favor some nuclei over others. Still, the overall pattern tells us that these particles are sampling the same chemically enriched galactic environment that eventually produced the Sun, the planets, and us. In other words, the incoming matter is not from some exotic separate universe. It belongs to the same broad family of stellar leftovers and recycled interstellar material that shaped our local cosmic neighborhood. That makes every measurement feel intimate. The particles are extreme, but the matter itself is familiar. Even at tremendous speed, it still carries the chemical accent of home. Cosmic rays can be accelerated again and again, gaining energy in steps. Not every particle receives its full power in one dramatic burst. In many models, the rise to high energy happens gradually, through repeated encounters with moving magnetic structures or shock regions. Each pass gives a particle another chance to gain a little more speed. Most fail to stay in the game long enough. They escape, scatter away, or lose energy elsewhere. A lucky few keep returning and keep climbing. This stepwise growth makes the process feel less like a single explosion and more like a relentless contest, where only certain particles remain trapped long enough to be promoted to extraordinary energies. That idea is deeply satisfying because it gives nature a believable path from ordinary matter to astonishing motion. You do not need a magical single kick. You need a rough environment, a strong magnetic setting, and repeated opportunities. The particle becomes a survivor of many encounters, carrying the accumulated reward of every successful crossing. The galaxy's magnetic field acts like a maze, delaying cosmic rays for ages. A straight line across the Milky Way would already be an enormous journey, but many charged particles do not get that luxury. They move through magnetic fields that twist, loop, and vary from place to place, which means their paths become tangled and indirect. Instead of heading cleanly from source to Earth, they wander, curve, and scatter. The delay can be immense. A particle may spend far longer meandering through the galactic maze than it would need if space allowed a direct route. This wandering changes the meaning of arrival. The particle reaching us today is not necessarily fresh from a recent event. It may have spent ages lost in the magnetic architecture of the galaxy before finally finding its way into our local region. That transforms the Milky Way from a simple backdrop into an active labyrinth. Space between stars is not only distance. It is a structured obstacle course, and these travelers often reach us only after a very long and winding detour. Some cosmic rays arriving today may have wandered the Milky Way for millions of years. But timescales involved can be astonishing. Because charged particles do not follow neat, direct routes, some may spend millions of years diffusing through the galaxy before reaching our corner of it. During that time, stars are born and die, clouds move, and whole regions of the Milky Way slowly change. Yet the particle keeps wandering. It is an extraordinary thought. Something that touches Earth now may have begun its journey long before modern humans existed. By the time it arrives, its source environment may already look different from what it was when the particle first escaped. In that sense, these visitors are late messengers. They are not giving us a live report from the universe. They are delivering information that has been delayed by a slow, tangled voyage through magnetic space. The particle is small beyond imagination, yet the span of time tied to its journey is geological and historical in human terms. It arrives carrying patience itself. Their long journey means cosmic rays carry a slow, ancient message. Light can also take ages to reach us, but for charged particles, the delay is often even stranger, because the route itself is scrambled. That means the message they carry is ancient, not only because the distance is vast, but because the path was inefficient and prolonged. By the time one arrives, it may be reporting on conditions from a far older chapter of the galaxy than its detection date suggests. This gives cosmic rays a haunting quality. They are messengers from astrophysical events, yet they do not speak in real time. They arrive after wandering, altered by travel, still useful but undeniably old. Scientists must interpret that message with care, reading clues about origin, composition, and transport all at once. There is something beautiful in that challenge. These particles are not hurried correspondence. They are drifters, bearing delayed testimony. Each one reaches us after a journey so long that it turns a brief detector signal into a fragment of deep galactic memory. Cosmic rays can fragment in space, creating lighter elements like lithium and boron. Some white elements are comparatively rare in ordinary stellar production, yet they appear in noticeable amounts among cosmic rays. That is because they can be made along the journey itself. When heavier nuclei such as carbon or oxygen smash into interstellar matter, they can shatter into smaller pieces. Among those fragments are elements like lithium, beryllium, and boron. This process is called spallation, and it means travel through the galaxy is not only a matter of motion. It is also a matter of transformation. The particle population changes as it moves. A nucleus launched as one element can contribute to the production of another after a violent collision in space. That gives cosmic rays an almost sculptural quality. Their identities are chipped and recut by impacts along the way. The galaxy is not only transporting matter, it is modifying it. Some of the lighter nuclei scientists detect are evidence that the road itself has been breaking heavier travelers into new atomic forms. Those fragments help scientists estimate how long cosmic rays travel before reaching us. Because certain light nuclei are produced when heavier ones break apart during travel, their abundance becomes a kind of clock. If the journey through interstellar space were very short, there would be fewer chances for those collisions, and fewer fragments would be made. If the journey were long and collision-filled, more secondary nuclei would build up in the population. By comparing the amounts of primary and secondary species, scientists can estimate how much matter the particles crossed and how long they likely spent wandering the galaxy. It is a subtle method, and that is part of its charm. No stopwatch follows the particle. No map traces its exact route. Instead, the traveler arrives carrying evidence of how much rough treatment it endured. Those chemical bruises become timing information. The particle's composition is not only a record of where it came from. It is also a record of how long the universe kept it on the road before letting it reach Earth. Cosmic ray composition changes with energy, hinting at different sources. The mix of incoming particles is not perfectly constant across all energies. As scientists examine different energy ranges, they find that the balance of light and heavy nuclei can shift, and that suggests the story may not have a single origin. Different classes of sources may dominate at different energies. Some accelerators may be especially good at launching lighter particles, while others may favor or retain heavier nuclei long enough to push them higher. Transport through the galaxy may also reshape the pattern. The result is that composition becomes a clue to cosmic geography and to astrophysical mechanism at the same time. It is like hearing a crowd change tone as the distance grows and realizing more than one group is singing. These changes do not solve the mystery by themselves, but they strongly imply that one simple source class is not enough for the whole spectrum. The particle population evolves with energy, and that evolution points toward a more layered universe. A rare cosmic ray can strike the eye, causing astronauts to see light flashes. Astronauts have reported brief flashes of light, even when the cabin is dark and their eyes are closed. One explanation is wonderfully strange. A fast particle can pass through the eye or nearby visual system and leave enough disturbance to trigger the sensation of a flash. Nothing has lit up the room. No lamp has turned on. The signal is being created inside the body by an invisible visitor from space. On Earth, our atmosphere and magnetic shielding reduce the chance of noticing such effects. But in orbit and beyond, astronauts are living in a more exposed environment that turns a cosmic process into a direct human experience. A particle born in some violent region of the universe may end its journey as a momentary spark in a person's vision. It is one of the most intimate encounters in all of space science. The cosmos does not only strike instruments. Sometimes it taps directly on perception itself. Cosmic rays can create background noise in sensitive cameras and telescopes. When a detector is built to catch faint light from distant objects, it is also vulnerable to things it was never meant to see. A fast particle passing through a camera sensor can leave a bright streak, a hot pixel, or a sudden burst of signal that has nothing to do with the target under observation. For astronomers, that means the raw image is often a mixture of true cosmic beauty and unwanted interference from other cosmic visitors. The irony is delightful. A telescope pointed toward the universe can have its view interrupted by the universe in an entirely different form. Researchers learn to remove these marks through repeated exposures, clever software, and careful comparison between images. Yet the contamination itself is a reminder of how active the environment really is. Even in the quiet act of collecting starlight, energetic particles are crossing the instrument and leaving their own little signatures in the data. Even your phone camera can sometimes catch a cosmic ray streak by chance. Most people think of cosmic ray detection as the work of giant observatories, but there is a humbling twist. The sensor in a consumer camera can occasionally register an energetic particle as a strange bright mark or speck. It will not happen often in ordinary use, and it is easy to mistake such artifacts for electronic noise or defects, but the possibility is real. That means a device sitting in a pocket or on a bedside table contains material sensitive enough to be touched, now and then, by events linked to the wider cosmos. The result is not a full scientific reconstruction of the incoming particle. It is more like a tiny accidental postcard. Still, the idea has real charm. The boundary between advanced astrophysics and everyday technology is thinner than it seems. A particle from a distant process can leave a fleeting trace in a tool built for family photos, messages, and ordinary human life. The cosmic ray rate at sea level changes with air pressure and weather patterns. The ground-level particle rate is not perfectly fixed from day to day, because the atmosphere above you is not perfectly fixed either. When air pressure rises, there is effectively more atmosphere pressing overhead, which means incoming cascades must push through a greater amount of material before reaching the surface. That extra burden can reduce the number of certain secondary particles detected below. When pressure falls, the count can climb slightly. Temperature structure higher in the atmosphere can matter too, because it affects how some particles are produced and decay as showers develop. None of this turns weather forecasts into cosmic drama, but it does reveal a subtle connection between everyday atmospheric conditions and high-energy events from space. The sky's ordinary moods help tune the background particle rain that reaches the ground. A barometer and a cosmic ray monitor are not watching separate worlds. They are reading different parts of the same layered atmosphere. During strong storms, the electric field overhead can influence particle behavior slightly. Thunderstorms do more than move rain and stir the air. They build enormous electric fields inside clouds, and those fields can affect charged particles passing through the stormy region. The changes are usually subtle rather than dramatic at the ground, but detectors have shown that shower particles can be accelerated or slowed in ways that alter what instruments record. In some cases, the atmosphere becomes a temporary natural laboratory where weather and particle physics overlap. This is a beautiful meeting of scales. A process born in deep space descends into a thundercloud, and the local electric field nudges the final act. Scientists study these effects because they can reveal how storms structure charge, and how atmospheric electricity interacts with high-energy particles. It is one more reminder that the sky is layered with different kinds of activity at once. Weather is not isolated from the cosmic environment. Under the right conditions, the two briefly touch. Some researchers explore links between cosmic rays and clouds, but evidence is debated. The idea is easy to find. Others have suggested hints of a connection under certain conditions. Others have found the effect too small, too inconsistent, or too entangled with other climate factors to support strong conclusions. What makes this topic fascinating is not that it offers a simple answer, but that it shows how careful science has to be when the atmosphere is involved. Clouds depend on moisture, temperature, aerosols, winds, and many interacting processes. Adding cosmic rays to that picture is plausible in principle, yet difficult to prove decisively in the real world. It is a good example of science at work near uncertainty. The question is interesting enough to pursue, and stubborn enough to resist easy storytelling. Cosmic rays are used to test detectors meant for future space missions. Before a detector is trusted on a spacecraft, engineers want to know how it behaves in a real particle environment. Cosmic rays offer a convenient and meaningful test. They provide a natural stream of energetic particles that can reveal whether an instrument measures accurately, responds too noisily, or suffers from unwanted sensitivity in certain conditions. This is especially useful for systems that will later operate in orbit or deep space, where radiation is part of everyday life. A detector can be taken to the laboratory, the mountains, or special facilities, but the natural background remains an important proving ground. In that sense, cosmic rays become instructors as well as hazards. They challenge new instruments before launch and expose weaknesses while there is still time to improve the design. The process feels fitting. The same environment that future missions must survive is already available, at least in part, to help train their hardware before the journey begins. They also help calibrate particle instruments on Earth, providing a free natural beam. Particle physicists often rely on specialized beams from accelerators when they need well-controlled tests, but nature provides a useful beam of its own at no cost. Cosmic rays arrive continuously, and that steady stream can be used to check alignment, timing, efficiency, and response in many kinds of detectors. Because some particles pass through matter in predictable ways, they are especially helpful for confirming that an instrument is behaving as expected. This does not replace precision beam facilities when exact conditions are needed, but it gives researchers a valuable everyday reference. The charm lies in the contrast. A highly engineered detector may cost a fortune and involve years of design, yet part of its validation can come from simply standing under the open sky and letting the universe do the work. The arrangement feels almost generous. Space sends particles freely, and scientists use them as a constant calibration source for the tools built to study nature more closely. In high mountains, cosmic ray detectors can catch more particles with less atmosphere. Altitude changes the whole experience of these particles. On a mountaintop, there is less air above the detector, which means the showers from space have been filtered and diluted less than they would be at sea level. More particles survive to reach the instrument, and the signals can be stronger or easier to study depending on the experiment. That is why high mountains have long attracted researchers interested in atmospheric cascades and related phenomena. The setting offers a compromise between ground access and a much more exposed particle environment. You do not need to leave Earth to move closer to the action. Sometimes you only need to climb. There is also a certain romance in the geography. Peaks already feel like places where Earth meets sky more directly, and in this case, the feeling is scientifically true. A detector on a mountain is living under less atmospheric protection, and therefore hearing a louder version of the cosmic rain. The Himalayas and Andes are natural laboratories for cosmic ray research. Some mountain ranges are so high, broad, and remote that they offer exceptional conditions for studying the particle environment above Earth. The Himalayas and the Andes stand out not only for their scale and beauty, but for the scientific opportunities created by their altitude. Instruments placed there operate beneath less atmosphere than most ground-based sites, which makes them valuable for tracking shower particles, solar events, and radiation changes with height. These regions also let scientists compare conditions across different geomagnetic locations, climates, and elevations. The mountains become more than scenery. They become part of the experiment. Human observers climb into some of the harshest landscapes on Earth to study invisible processes arriving from beyond Earth, and that meeting feels almost mythic. Ancient stone, thin air, and high-energy particles all come together in one place. A summit observatory is not just closer to the stars in feeling. It is measurably closer to the physics arriving from them. Cosmic rays can trigger nuclear reactions in aircraft materials over long periods. High above the ground, aircraft spend years moving through a particle environment stronger than the one at sea level. Most of the time, nothing dramatic happens. Yet over long periods, those fast particles can strike the atoms inside the plane itself and trigger rare nuclear reactions. In effect, the aircraft becomes a target as well as a vehicle. Tiny changes can accumulate in metals, electronics, and other materials, producing trace amounts of new isotopes that were not there before. These effects are usually subtle and carefully studied rather than alarming, but they are real enough to matter in long-term engineering and radiation assessment. It is a remarkable thought. A plane carrying passengers through ordinary daylight is also passing through a field of invisible projectiles, energetic enough to alter matter atom by atom. The journey through the sky is not passive. Even the body of the aircraft is slowly being written on by the high-energy environment around it. They can also activate rocks and soil, creating tiny traces scientists can measure. When energetic particles strike atoms in exposed rock or soil, they can transform some nuclei into rare isotopes that accumulate over time. These traces are usually tiny, but with careful laboratory methods, they become extraordinarily useful. Scientists can measure them to estimate how long a boulder has sat at the surface, when a glacier retreated, how quickly a landscape is eroding, or when a landslide exposed fresh material to the sky. This means the ground beneath your feet can carry a clock, set not by human hands, but by continual bombardment from above. A mountain ridge, a desert stone, or a piece of ancient bedrock can all preserve a record of exposure to the particle rain from space. It gives geology a surprising cosmic dimension. The shape of valleys and slopes is not read only from layers and fossils. It can also be read from faint isotopic signatures produced by high-energy visitors striking Earth over immense spans of time. Cosmic ray muons can map hidden chambers inside volcanoes by absorption patterns. A volcano may look solid from the outside, but inside it can contain conduits, denser plugs, fractured zones, and pockets where magma once moved or may move again. Muons offer a way to probe that hidden interior without cutting into it. The method works by measuring how many of these particles arrive from different directions after passing through the mountain. Thick, dense rock blocks more. Less dense regions allow more through. By comparing those counts, scientists can build images of internal structure in a way that resembles a natural form of X-ray vision on a colossal scale. This is one of the most thrilling examples of cosmic rays becoming practical tools. Particles created high in the atmosphere descend through a volcano, and the pattern of what survives reveals what human eyes cannot see. The mountain stays closed, yet the hidden architecture begins to emerge from a patient reading of invisible traffic passing through stone. This technique helps assess volcanic risk without drilling into dangerous slopes. Volcanoes are among the most difficult places on Earth to investigate directly. They can be unstable, steep, gas-rich, and prone to sudden change, which means drilling or deep intrusion is often risky, expensive, or simply impossible. Muon imaging offers another path. By placing detectors in tunnels, shelters, or carefully chosen positions around the volcano, scientists can monitor changes in internal density over time. That can help identify blocked pathways, growing voids, or regions where material has shifted in ways that may matter for future activity. The method does not predict eruptions on its own, and it is usually combined with seismic, thermal, and gas measurements. Even so, it adds something rare and precious: a direct look into the body of the mountain without forcing entry. That makes the technique feel both elegant and respectful. The volcano is not broken open for answers. Instead, the sky supplies the particles, and the mountain reveals itself by what it lets through. Cosmic rays helped inspire the idea that space is not empty, but active. Before their discovery, it was easier to picture the space around Earth as a mostly empty backdrop, interrupted by sunlight and little else. The realization that energetic particles were constantly arriving from above changed that vision profoundly. Suddenly, the heavens were not only a place to look at. They were a place that acted on us. Space contained invisible traffic, real energy, and ongoing processes capable of reaching the atmosphere and influencing matter below. This shift was larger than one scientific result. It altered the emotional meaning of the sky. The world above became dynamic, populated by forces and messengers that did not need to shine to be real. In modern science, that idea feels natural, yet it had to be learned. Cosmic rays helped teach it. They showed that between stars and planets, there is not mere silence. There is motion, structure, and exchange. The universe is not only visible in light, it is physically active all around us. Their discovery changed our view of Earth as a planet under constant bombardment. For most of human history, the ground felt stable and the sky felt distant. The discovery of these particles blurred that separation. Earth was no longer just a world illuminated by the heavens. It was a world being struck by them, continuously and from all directions. That did not mean catastrophe. It meant connection. The atmosphere became understood as a battleground of collisions, where incoming particles were constantly meeting the air and producing cascades overhead. The surface remained safe, largely because natural shielding was doing its work so effectively. This new perspective made Earth seem at once more vulnerable and more wondrous. Our planet is not isolated from cosmic events. It is immersed in their consequences. Even on the calmest day, a hidden exchange is underway between Earth and the wider universe. That realization expanded both science and imagination. Home became part of a larger physical system, open to influence from deep space every moment. Cosmic ray research connects astronomy, geology, climate science, and medicine. Few scientific subjects roam as freely across disciplines as this one. Astronomers study the sources and journeys of the particles through the galaxy. Geologists use cosmogenic isotopes to date landscapes and exposed rocks. Atmospheric scientists examine how the particles interact with air, chemistry, and electrical processes. Medical and space health researchers study radiation exposure in aircraft, orbit, and future deep space travel. Even archaeology and volcanology find uses for muons and isotope records born from the same cosmic process. What makes this so beautiful is that the particles do not respect the borders humans draw between fields. They move from exploding stars to interstellar gas, from the atmosphere to living tissue, from mountain slopes to laboratory instruments. Following them forces science to become connected too. One topic opens doors into many others. That gives the subject an unusual richness. To study these arrivals is not only to study astrophysics, it is to trace a thread that runs through many parts of the natural world. The story of cosmic rays is a story of particles, but also of space itself. At first glance, the subject seems to be about tiny objects moving very fast. That is true, but it is only the beginning. To understand these particles, you also have to understand the environments they cross. Magnetic fields matter. Interstellar gas matters. The solar wind matters. The atmosphere matters. Even ancient background light spread through the universe can shape what eventually arrives. In that sense, each particle is a probe of the medium it traveled through. It carries evidence not only about where it may have been born, but about the space between there and here. That is why the topic feels so large. You begin with something smaller than an atom, and soon you are talking about the structure of the galaxy, the history of the universe, and the hidden architecture of near-Earth space. The particle is the messenger, but the deeper message is about the nature of the vast regions it has crossed. Every cosmic ray that hits you began as energy in a distant cosmic event. Before it became a particle crossing your body, it was part of something larger and more dramatic. Perhaps it was energized in the shock of an exploding star. Perhaps it was accelerated near a compact object with violent magnetic fields. Perhaps it joined a long chain of interactions that began in a region of space so remote it has no familiar name in ordinary life. Whatever the source, the particle that arrives here carries energy that was once bound up in some astrophysical event far from Earth. That makes the encounter strangely intimate. A process that unfolded across immense distance and scale can end in a brief passage through skin, air, water, or stone. The body never notices. The world does not pause. Yet the connection is real. The universe is not only observed from a distance. Its energetic history is constantly arriving in physical form, touching the planet and everything on it in ways both subtle and profound. In a quiet way, cosmic rays remind us the universe touches us constantly. They do not announce themselves with color, thunder, or a sound in the room. Most arrive unnoticed, pass through the atmosphere, and leave only traces in detectors, electronics, chemistry, or the occasional flicker in a sensor. Yet their silence is part of what makes them so moving. They reveal that contact with the cosmos does not require spectacle. It is already happening. Earth is not cut off beneath a sealed roof. It is open to a continuous exchange with events far beyond the reach of our senses. These particles link daily life to exploding stars, black holes, solar storms, ancient light, and the magnetic structure of the galaxy. They make the ordinary world feel more connected without making it less safe or familiar. That is the lasting wonder of them. Even in stillness, even in darkness, even during the most uneventful moment, the wider universe is present here. It is reaching us, touching us, and leaving its faint signature behind. As we come to the end of tonight's journey, it is worth pausing for a moment and remembering just how extraordinary this quiet rain from space truly is. We began with particles born in some of the most powerful places in the universe. Exploding stars, turbulent magnetic storms around black holes, vast regions of the galaxy where matter is hurled outward at almost unimaginable speeds. From those distant events, tiny messengers set off on journeys that can last for millions of years, wandering through tangled magnetic fields and the dark spaces between stars. Eventually, a few of them reach our planet. They strike the atmosphere high above the clouds, spreading into cascades of new particles that ripple through the sky. Some flash briefly in detectors. Some pass through mountains or deep water. Some leave traces in ancient ice, in tree rings, or in the rocks beneath our feet. A few may even pass silently through you, unnoticed, after traveling across the galaxy. It is a remarkable thought. The same universe that shines in the night sky is also quietly touching our world every moment, sending these tiny travelers across unimaginable distances until their journeys end here. And now, as the story settles, you can let your mind do the same. Allow the images of distant stars and long cosmic journeys to drift gently away. Let your breathing slow. Let your thoughts grow softer, like particles spreading quietly through the atmosphere. If you enjoyed this peaceful exploration of cosmic rays, feel free to like the video, subscribe to the channel, or share a thought below. It helps more curious minds discover these sleepy journeys through science. And if you happen to still be awake, another calm adventure is waiting for you on the screen. But for now, you can simply rest. Sleep well, and good night.